Hey, so this demo for the enhanced passphrase generation using recurrent neural network on top of a pool of millions of words with some linguistic rules in between the model and the pool to make sure that only pronounceable words emerge um, and pronounceable in the given language, but that there is no limit on what words will emerge. And so this gives it, removes the uh, list that's normally included with these schemes, with the passphrase generation schemes, like BIP39 in Bitcoin or EFF's dice, where they both include lists, and those lists, range from 2,000 to 8,000 words and giving you entropy of 11 to 13 bits per word. With the in case of dice where it plays a little trick to add one extra bit of entropy, but it's still not enough because you'll need 9 words to hit the 128 barrier, or 8 words, and that's over the 8 words to go over 100. So that's still the that's still not a number of words that you can hold in your mind and take around and remember, from device to device. So, psychologists say the maximum number of words that a person can remember is 7 words. In our case, we want to keep it 5 words or less. I feel that 3 words is perfect, and 3 words give us, at the very least, at minimum, worst case scenario, 69 bits of entropy. But in reality, it's a lot more than that. It's a lot closer to 100 bits or over 90 bits of entropy anyway, because the um, list is not known, and we're grabbing from all the words that exist out there on the web, and having millions of words, and then filtering the ones that are pronounceable, ones that have the right number of syllables, the ones that don't have any foreign sounds, the ones that keep the semantics flat, and memorable, allows random sequence to be still memorable. Let's try another one, for example, here. This is from the same set, from the same exact set that was downloaded, because you don't download all the millions of words out there, but set. As you can see, it's people's names, towns names, yeah, that's an easy one for me to remember personally. And so these words, again, come from a pool of millions. All the words that are out there, all the pronouns, brand names, foreign pronouns, foreign brand names, concepts, things, abstract, literal, virtual, that haven't made it into any dictionary, including Wiktionary. By the way, Wiktionary alone has 6 million entries, so there are millions of words out there, millions, and basically we narrow it down to the ones that can be pronounced easily, and then we feed that into a recurrent neural net that is tweaked to spit out even more words, augmenting the pool, and the words it spits out are pronounceable, easy to remember, but they have no meaning. They don't exist. It could be, Apkosh is a foreign name, but it could have been also AI generated, and you wouldn't know the difference. So at least one of those is, we can add this rule that says, one of these has to be AI generated, or we can just rely on the fact that we're starting with millions of words, and even without the AI augmentation. And so, the AI augmentation is the second phase of this experiment that we're going to show. But it's basically training right now and building a very good set that's growing into the 100,000s, eventually into the millions of new words that have no meaning but are pronounceable and easy to recall. And when we have this also ability to select the entropy. Nobody should really need 115 bits of entropy. 69 should be enough. Um, If the state wants to break down your encryption, 69 is doable. 115 would have them come to your door, knock down your door, interrogate you. The state will always get its way with you. So if you want to be stubborn and fight the system, you will be 115 bits is not going to protect you. There's a physical security has primacy over cyber security, and the state has a lot of physical power. So versus you, the individual. So I wouldn't really recommend that because that requires 5 words, whereas this requires 3 words. And if you wanted to go to 138 bits, that would be 6 words. Doing this with EFF's Electronic Freedom Foundation's Diceware requires you, to get to 115 requires you to have 9 words, which gets you to 128. But there's a huge difference between 9 and 5 words, and the magic number is around 7 for the maximum limit a person can remember reliably. Anyways, they're what they do in Bitcoin BIP39 and EFF Diceware that's troubling is that they, well, not intentionally, is that they include the word list with the algorithm. So if the attacker has the word list, it's just a permutation of those words, and then they, can spit out answers at 10 billion guesses a second or whatever they can afford on their GPU rigs. And, if they are sophisticated, they can do it in parallel, data parallel fashion, segments the search space and go at it in parallel. And so, it's good to have enough entropy, but hackers cannot really touch this number. It takes a major organization to break 69 bits of entropy, and that's just 3 words in this scheme. Because we're not including a list. The list is out there. It's every single word available. Plus, it's AI generated words, and so there's no way for anybody to actually compose a list. We say it's 23 because that's just the worst case scenario if somebody was to theoretically compile the same list, but it's impossible because it's literally all the words that are out there. We grab them on the fly as we're building the list, and we build a random set that's statistically sufficient to produce the random permutations for the passphrase, and that's how the system works. So if you enter an email address and register, you will notice that we have sorry, clear this. Let me do this again. I just deleted the console log for the objects. Okay, so it's building a list right now from over 800 million words, human AI generated, and then once it builds one, it found one that wasn't in any English language dictionary or any dictionary per se. Doesn't exist, for example, in Wiktionary.com, which has 6 million entries, including foreign names. So, and the future it will also make sure that one of the words is AI generated. That requirement is not strict right now. It may be AI generated, may not be, because we have a small set, growing set while the system is training. And this is just an early demo of it. So let's say Jodat Stargate Warren, that's my password. And I'm gonna register, and there I got the, let me expand that a little bit. Right, so I get the public key and the private key pair for encryption. And then I get the sign key as well as the secret sign key. And we basically sign the payload with the private key, and then we send our public key that has already been associated with our verified email The whole scheme is described in the presentation, so you better go through that. Otherwise, if I talk about it in a hurry, I may miss some of the details. It's implements application level security basically, and the idea behind passphrases is that you don't want to be encrypting these keys and taking them from place to place with you, from device to device. You want to be able to generate them by just remembering this, and you don't want the lazy you know uh, fox jumped over the cow or whatever that phrase is. The lazy brown fox jumped over something. Whatever it is that phrase is, if it's a known phrase, it has zero entropy. This phrase currently has zero entropy because it's been captured in this YouTube video, and many people will see it, and so don't use it. But you can easily just use the system once it's available, and generate many different. Oh, we've already registered, so we'll imagine we haven't registered yet. Yeah, and so all right, so this is a one-time process where it compiles all of this. And now you can, I like this one, so I decide to go ahead with it, and I get my keys, and this becomes my passphrase, mascot Kanban concept. And there's no way that any computer program can guess this because it doesn't have, Kanban doesn't exist in any dictionary. So even if it uses a dictionary, English dictionary with 500,000 entries, it still cannot do it. Even if it uses Wiktionary as a source with 6 million, well, then we're talking about 23-bit entropy per word with that huge a base. But still, it doesn't exist in its in Wiktionary, and therefore it cannot even guess it. It would have to resort to 27 to the power of the number of letters, and 27 because 26 letters and one extra for space. And so it would be close to 100 bits of entropy. We're talking about with 3 words, we can achieve 100 bits of entropy. Diceware requires 8 words for that. So 3 versus 8, that's a huge, humongous difference in terms of memorability, recallability. And Bitcoin's BIP39 requires 12 words to get to 128, 11 words to get to just over 100. And so, or 10 words just to get over 100, so difference between 8 or 10 words is humongous. So this is a huge, advancement in terms of state of the art. And we'll leave you with the presentation, and you can ask any questions.